These are the solutions to activity 6. So can we approximate the delta H of the below reaction using bond enthalpies? So the idea of bond enthalpies is what we want to do is we want to sum up the energy it takes to break our bonds here. So we're going to take N2 plus 2H2 to 2 nitrogen atoms plus 4 hydrogens. It takes energy to break bonds, so the delta H of this reaction here is going to be given by 941 kilojoules per mole times 1 mole of N2. So that's 941 kilojoules. And then we're going to add 2 times the 435 kJs per mole for the 2 moles of H2. So that means it takes 1,811 kilojoules to break the bonds in the reactants. And then we're going to get the energy back when we take the 2 nitrogens, the 4 hydrogens, we recombine them to have a nitrogen-nitrogen single bond. So that's 159 kJs per mole. There's one of that bond. And then there's 4 nitrogen-hydrogen single bonds. So I have 4 bonds that look like this. So I have 4 moles. Well, let me go to the product. Let me just write it out. NH2, NH2. And then the delta H here is going to equal 4 times 389. So 4 moles times 389 kJs per mole. And then plus the 159 times kJs per mole times 1 mole. So that's 1715. So 1,715 kJs. But I'm making these bonds, so this is exothermic. So breaking the bonds is plus 1750. So making the bonds is minus 1750 because I'm making bonds that's exothermic. So it's the sum of the bonds to break them in the reactants minus the sum of all those bond strengths in the products. So this is a weird delta H where it's the sum of the reactants bond strengths minus the sum of the products bond strengths. But we're adding these reactions up, canceling out our intermediates, leading to our desired reaction. And so we add up our delta H's. So we go 1811 and then plus negative 1715 gives us plus 96 kJs. So just be sure to account for how many moles of each of the bond types there are. We have 2 moles of H2, so we have to multiply this by 2 moles, 1 mole of N2, so it's by 1 mole. We had 4 moles of the NH bond, 1 mole of the NN single bond. Question 2, what is the frequency of a photon with a wavelength of 625 nanometers? If you go to the daily quizzes and look at the equation sheet, you'll see that there are some provided equations. And I'll try to mention these as we go along, that a provided equation that you'll get with midterm 3 is that C is equal to lambda times nu. You'll be given the value of the speed of light in the vacuum that we're using here. And so to calculate the frequency, it's going to be C divided by lambda. So 2.998 times 10 to the 8 meters per second, and then divide by 625 nanometers. I just have to convert nanometers to meter because the units of the speed of light. 1 nanometer is a 10 to the minus 9 meter. And so we work this out, and this ends up being 4.80 times 10 to the 14. Question 3, a photon with a wavelength of 2,500 nanometers is in what region of the electromagnetic spectrum? Well, the one I want us to know is that the visible is 400 to 750, and beyond red is infrared, and then beyond violet is the ultraviolet. And so we have the ultraviolet and then the infrared. This helps us remember this is the violet part of our spectrum. That's the red part of our spectrum. So 400 nanometers is violet light. 750 nanometers corresponds to red light. And so this is certainly not a UV photon, certainly not a visible. Radio frequency is going to be a lot longer wavelength, closer to the unit of meters. This is getting to wavelengths on the length of about meters, so really long wavelengths. So this is going to be most likely that infrared. I wouldn't worry too much about the cutoffs between the regions, but if you're relatively close, we're within an order of magnitude or so of the visible region, so we're definitely going to be in the infrared. So I'd also just generally know the gamma ray to X-ray to UV to visible, and then IR to microwave, and then radio frequency. So just knowing the general order here. Question 4, a laser emits an energy with an energy of 525 kilojoules per mole of photons. What's the wavelength of light? And so to calculate the wavelength of light, what we're going to need to do is to consider the energy per photon. So we need the energy of a single photon. We know that that's equal to h nu, or hc divided by lambda. So I have to figure out how many joules there are per one photon. And so we know the kJ is per mole of photon, so the number of joules per one photon, 525 kJs per mole of photons. 1 mole of photons, just like a mole of anything, it's 6.022 times 10 to the 23 photons. And then 1 kJ is 1,000 joules. And so the energy per photon is 525 kJs divided by Avogadro's number, 6.022 times 10 to the 23, and then converting the joules times 1,000. And so this works out to be 8.718 times 10 to the minus 19 joules. This is the energy per photon. So it's our photon energy. That's what we can plug in here, and then use Planck's constant along with the speed of light to solve for wavelength. So lambda is going to equal hc divided by the energy of our photon. And so what we're going to do next, or to solve for the problem, is take 6.626 times 10 to the minus 34, and that's joules times seconds, times the speed of light, 2.998 times 10 to the 8, and that's meters per second. So our per second cancels with the units there. And then we're going to divide by our energy in joules. So that's 8.718 times 10 to the minus 19 joules. Our joules cancels. We get our wavelength in units of meters. And so our wavelength will equal, let's see what it comes out to. So 6.626 times 10 to the minus 34 times 2.998 times 10 to the 8. Divide by that energy, I get 2.278, call it 2.28 times 10 to the minus 7 meters. We want this in nanometers. So multiply by 10e9, or multiply by 10 caret 9. Or, not by 10e9. Multiply this by 10 to the caret 9, or by 1e9. That gives us 228 nanometers. So we multiply by 10 to the 9, and we get 228 nanometers. Next question. So copper absorbs with a minimum frequency of 1.15 times 10 to the 15 hertz for an electron to be ejected. So this is telling us the ionization energy per one copper atom. So the energy it takes to ionize copper is 1.15 times 10 to the 15 hertz. We could calculate this in terms of an energy if we wanted. E is equal to h nu. So that's just telling us something about the energy it takes to remove an electron from this atom. What wavelengths of light are capable of causing this electron to be ejected? Well, what we want is the energy has to be this energy or greater. So we have to be, at this frequency or greater in order to have enough energy to cause that electron to be ejected. And so then if I take the frequency that has to be so big, then the wavelength is going to have to be some value or smaller to give us a larger. So we need to go to a lower wavelength to give us a higher frequency. So the wavelength associated with that specific frequency, I use the speed of light, so the frequency is equal to c over lambda. We want to solve for the wavelength here. So the wavelength is c over nu, and we want the nu value to be a certain value or larger, meaning that this requires that the wavelength be a certain value or smaller. So we take the speed of light, 2.998 times 10 to the 8, and then divide it by the frequency of 1.15 times 10 to the 15. That gives us a wavelength of 2.609 or 2.607 times 10 to the minus 7 meters, which is going to equal 261 nanometers. So we want the wavelength to be 261 nanometers or lower. So if we go to a lower wavelength than this, then we're going to go to a greater energy. Remember, the energy of our photon is equal to hc over lambda. So we want to go to lower wavelengths to go to greater energy, just like we want to go to greater frequencies to go to greater energy to cause that electron to be ejected. If we did the opposite, if we went to a greater wavelength than 261, we'd be going to too low of an energy to cause that electron to be ejected. So going to lower wavelengths is associated with greater energy of a photon due to that relationship there. Question 6, which transition of the H atom leads to the 411 nanometer line in the H atom emission spectrum? And so if we think of our H atom emission, this is one of the higher energy transitions. If you think of the transitions, the other 3 visible transitions of the H atom occur at transitions that are closer to the red portion of the spectrum, so lower energy. So this is likely going to be the greatest energy, and if you remember. So one way to sort of think about this problem is that we have these transitions taking place. We have the 6 to 2, the 5 to 2, the 4 to 2, and the 3 to 2 transitions. These are all the ones that are leading to emission of an electron, or emission of a photon from the change of the electron from a high energy state into a low energy state. So the atom is losing energy when it goes from the high state to the low state. And so we have the greatest energy that's going to be lost by the H atom. And so this is most likely going to be the one that leads to the 411 nanometer line. This one's going to be the lowest energy difference. And so this is probably going to lead the one that's closest to 750 nanometers in that visible region. So I think that one's around 650 or so nanometers. Now, how can we show this, or how can we double check that this is the wavelength? Well, there's a few ways that we can do that. We can either use the 1 over wavelength is equal to the Rydberg constant for hydrogen times 1 over the N1 squared minus 1 over N2 squared, where we plug in a 2 here and a 6 here. We use the Rydberg constant for hydrogen, and then that gives us the inverted wavelength, so then we can convert it to wavelength and see that it's the 411 nanometer line. We can also use the Bohr model equation that the energy is a function of n is equal to minus 2.18 times 10 to the minus 18 joules times 1 over the n value squared for that electron. And then we can calculate the delta E for the H atom, the delta E for the H atom by taking the energy of the final state minus the energy of the initial state. So let me use this equation here, because I like using this equation because I get my delta E for the H atom, and it helps me try to understand what's really going on here in a better way than I think we get with this equation. So yeah, you can use this equation and look up that constant, solve for the wavelength, and it works. But I like using the delta E equation because what I can do is I can plug in minus 2.18 times 10 to the minus 18 joules times 1 over the final state. So the final state would be 2. And then subtract negative 2.18, because I'm taking the difference, the delta E is the final minus the initial. So I'm then just plugging in the initial energies, minus 2.18 times 10 to the minus 18 joules times 1 over the initial values of 6 squared. And so then this leads to the H atom going through a loss of energy. So 2.18 times 10 to the minus 18 times 1 divided by 2 squared, and then minus negative 2.18 times 10 to the minus 18 joules times 1 divided by 6 squared. And I do this math here, and I see that the delta E for the H atom is minus 4.84 times 10 to the minus 19 joules. So this is the energy that's lost by the H atom as it goes from a high energy state to a low energy state. The energy lost by the H atom is equal to the energy gained by the photon. And so I just like to kind of see and think that you have this kind of system versus surroundings relationship like we saw in chapter 5 a lot, where you have the atom undergoing a loss of energy, has a negative energy. So our photon energy here is equal to plus 4.84 0.84 times 10 to the minus 19 joules. And that's the energy that goes into creating the photon. That's equal to hc divided by lambda. And we solved that problem earlier, but we can calculate our lambda by taking hc divided by that energy. And then, so let's just do this. I'm just going to say it out loud, but 6.626 times 10 to the minus 34 times 2.998 times 10 to the 8, then divide by that energy. That gives us 410 nanometers. Gives us negative, well, I haven't got rid of the minus sign in my calculation, but the positive energy here gives us a value of 4.1, maybe there's some goofy writing, we get 4.10 times 10 to the minus 7 meters, which is equal to 410 nanometers. So this is the transition here that's leading to that 6 to 2 transition. Now, a few things. One, like we went into this problem kind of presuming or guessing or having a good educated guess that the end value would be 6 here. If you weren't sure, we could have left this as a variable, and then we could have calculated the delta E that would have to be the case for the H atom undergoing a 411 nanometer transition. So we could have calculated this energy from this wavelength of light and said, well, what would the energy, the H atom that it would have lost been equal to, and plug that in up here and then solve for the 6 as a variable. So there's a few different ways you can think through solving this problem, but to me, a lot of these problems become pretty conceptual of, can you set up and think about the relative transitions of the H atom? Remember, the visible ones all end in 2, the UV ones all end in the 1 value, because relatively speaking, I'm going to draw a weird line in here, but the N equals 1 is a lot lower in energy compared to the N2, so all the transitions of 6 to 1, 5 to 1, 4 to 1, etc., those are all in the UV region. All the transitions that end in 3 are in the UV, or excuse me, are in the IR region. So your 6 to 3, 5 to 3, 4 to 3 are all in the IR region, the infrared region. And then you can even have 7 to 2, 8 to 2, but those just become higher energy. Those start to fall into the UV region. So just trying to be mindful of how we got into this problem was seeing 4 distinct transitions from the H atom in the visible spectrum, the visible part of the spectrum. And those ended up being from the 6 to 2, 5 to 2, 4 to 2, 3 to 2 transitions. So this question's here very similar, but it's kind of just a more conceptual based question, because it says which transition below for an electron in an H atom leads to the emission of a photon with the greatest wavelength. Okay, so our choices here, 3 to 2, let me draw this roughly to scale. So the idea for the H atom, an important thing, like on a conceptual side, is the N equals 1 to 2, difference of energy very big, N equals 3 smaller, 4, 5, 6, 7, we're approaching infinity as we go up in N value. So when we think of these N values, 6 to 2 versus 3 to 2, the 6 to 2 difference of energy is greater, and then these two transitions here lead to emission, light to be emitted. And then if we want to do the opposite, if we want to go 2 to 3 or 2 to 6, this requires the absorption of energy. So we got to absorb energy to go upward. So absorption's upward. So the 2 to 3 or the 2 to 6 aren't going to be the answer, because these lead to absorption, the absorption of light, not the emission of light. And then these two here are the ones that lead to emission. Light's emitted here. And then we're going to have a higher energy emitted by the 6 to 2, lower energy by the 3 to 2, and a lower energy transition corresponds to a greater wavelength. So the greater wavelength transition here is the 3 to 2. The lower wavelength transition that we saw previously with the math worked out was the 6 to 2. Question 8. Which of the following sets of quantum numbers are allowed by an electron in an atom? So we have the idea that the lowest N can be as 1, and it has to take on whole numbers on upward. L's range is it can be as low as 0, and then whole numbers, but only up to the N value minus 1. The M sub L has the range of whatever the L value is, negative, through 0, all integers between, and then all the way to plus L. And then the M sub S is always equal to plus or minus a half. And so the idea here is that the N is telling you about the size of the electron, L about the shape of the orbital it resides in, M sub L is about the orientation of the orbital, or how many orientations there are possible. It tells you about the number of orbitals that share the N and L value. And then the M sub S is about the spin up or down, because we can have 2 electrons in each orbital. So specifying all 4 together tell you about an orbital, or about an electron in an orbital. N, L, M sub L together about an orbital, N and L together tell you about a subshell, and the N value is what we call the shell. Okay, and so then a few examples that don't have anything to do with this example yet would be that if N is, say, equal to 4, then L could be equal to 0, 1, 2, or 3. The M sub L depends on which of these L's you have, but if you're the L0, the only M sub L is 0. The only M sub L is possible for 1 is -1, 0, +1. If your L is 2, -2, -1, 0, 1, 2. If your L is 3, -3, -2, -1, 0, 1, 2, 3. But the number of those M sub L's tells you how many orbitals can share that N and L. So if you just take, for example, having an N equals 4, L equals 2, this is telling you that you have the D-shaped orbitals, because that's what the L2 means. So the S is the S is 0, P is 1, D is 2, F-shaped orbitals are 3. And then, so a 4D subshell is comprised of 5 orbitals. Why 5 orbitals? Because you have 5 M sub L values. So just a quick little detour on kind of a few details about quantum numbers. But which set here is not possible? This M sub L here is not possible because L is 1. You can have an L of 1 when N is 3. That's legal. But you can't have an M sub L of -2 when L is 1. The range of M sub L is -L to +L. So the only values M sub L can be when L is 1 is -1, 0, or +1. When we have an L of 2, or excuse me, when we have N2, we cannot have L2. The range of L is up to N -1. So when N is 2, we can only have an L of 0 or 1. So neither of those are allowed quantum numbers for an electron in an atom. What is the designation for the subshell with the N equals 4, L equals 2? I already kind of mentioned this in the previous slide, but this would be the 4D subshell. The 4S would have an L of 0, the 4P an L of 1. And then there's 5D orbitals because of the range of the M sub L's. So the range of the M sub L's is telling you about the direction of the orbital, but it's really telling you how many orbitals can share that combination of N and L. So you get 1, 2, 3, 4, 5D orbitals. So some lingo here would be there's 5 orbitals that comprise the 4D subshell. So 4D is a subshell, 4S is a subshell, but there's just 1 orbital within the 4S. There's 3 orbitals within the 4P subshell. Question 10, what is the maximum number of electrons that can occupy the 5F subshell? So the 5F subshell is the N equals 5. F means L is equal to 3. And so the possible number of M sub L's here is -3, -2, -1, 0, 1, 2, 3. That's 7 values, that's 7 orbitals. M sub S for each of those orbitals can be equal to plus or minus a half. So I can have spin up, spin down. So in other words, I have 7 orbitals, 1, 2, 3, 4, 5, 6, 7. I can go spin up, that's 7, and then 8, 9, 10, 11, 12, 13, 14. So I get 14 electrons into the 5F subshell because there's 7 orbitals, 2 electrons per orbital. Question 11, what is the range of possible magnetic quantum numbers, the M sub L's, for this orbital below? This is a d orbital. I can tell it's a d orbital because it's a double set of lobes. There's sort of the number of axial nodes. We talked about this briefly, but the number of nodes that separate the orbitals is 2. So I have 2 axial nodes. So that's going to give me the D-shaped orbital. And so the M sub L range here is -2, -1, 0, 1, or 2. I don't know which one it is, but it's one of those. The M sub L's can range all the way from the range of here, because that's the range for when L is equal to 2, given by the shape of that orbital. How many unpaired electrons does a sulfur atom contain? So sulfur's ground state electron configuration would be the neon configuration, followed by a 3s2, 3p4. Just look at the periodic table to see that we're in the row after neon. So neon's configuration 1s2, 2s2, 2p6. So we can condense the configuration of sulfur down to here. And if we're thinking of the entire configuration, I could be thinking the 1s, the 2s, the 2p set of orbitals, the 3s, and then the 3p. So think of these orbitals here this way. And so I fill the 1s2, 2s2, 2p6. I should probably fill it this way or think of filling it, spin up first and then spin down next, and then 2 here, and then my final 4 electrons go 1, 2, 3, spin up, and then spin down for the last. So this is following Hund's rule. So maximize the spin when filling into a subshell that's not completely filled. So that gives us 2 net unpaired electrons. Question 13, which atom contains a total of 4 valence electrons? So when we look at an atom like carbon 1s2, 2s2, 2p2, the valence, or the outermost shell, and then if we have an unfilled lower subshell, we got to count those 2. I'll give you an example of that in a minute. But for carbon, that doesn't matter. I just have the outermost shell is n equals 2. So this is our shell. The shell is the n value. So I have 2 orbitals that are sharing our 2 subshells that are sharing the outermost shell, the n equals 2. So I have 2 plus 2, that's 4. So I have 4 valence electrons for carbon. And then tin and lead are in the same group as carbon, so they have to have 4 as well. And so all of these are going to share having 4. So if you look at carbon, it has 4. The entire row of carbon has 4. Excuse me, the entire column of carbon has 4. If you count nitrogen, nitrogen has 5. The entire column of nitrogen has 5. The halogens, if you count fluorine, it has 7. The entire column of the halogens, they all share having 7 valence electrons, even the larger atoms. And so when you start looking at like an atom, like let's think about manganese, for example. It's a 4s2 3d5 on top of the argon configuration. It would have 7 valence electrons. If I get all the way across to zinc, zinc has a 4s2 3d10. I stop counting these towards the valence once that's completely filled. So we have 2 valence electrons for zinc, and if I go to gallium right next to it, gallium's a 4s2 3d10 4p1, and so this is sharing the configuration of aluminum, so we end up having, again, just 3 valence electrons. So I can count an unfilled subshell until it's filled. So the outermost shell plus anything in the lower subshell that's unfilled. Question 14, an atom has an anomalous configuration of 5s1, 4d5. What is the element? And so I just go to the periodic table and try to find the element that has kryptons count that's 36 electrons, and then plus, zoom in to make sure I'm seeing that as the 5. So I'm going to add 6 electrons to that. So I'm looking for element number 42. So what element has 42 electrons? Just check your periodic table, and that would be molybdenum. So this is molybdenum. And then how many unpaired electrons? I have the 5s1, and then the 4d, which there's 5 orbitals, so I have 5 of the 4d spin unpaired, so 6 total unpaired electrons. Last question, what is the ground state configuration of neodymium? We're told it doesn't have, just assume that an atom is not anomalous, that it doesn't have one of these goofy configurations that you're not expecting. And so neodymium is all the way down in the lanthanide series. It's sort of after cerium, so it's element number 60 as well. So sometimes it's helpful to know that this is 60 neodymium, so we should be coming up with 60 electrons. So I have a xenon, the nearest noble gas, it's 54 electrons, and then followed by a 6s2, so we're in the 6th row, so you just count down to the next element after xenon, so that's the 6th row, so it's a 6s2, and then we start filling into the first F subshell. And so we're filling into the 4F. The first time you can have the F is when L is 3. So that's our 4F subshell. And then we're going to have 4 electrons into that subshell. And so if I take 54 plus 2 plus 6, that gives me 60 total electrons. If I count across from after barium, neodymium is the 4th element past barium. So 4 electrons into the 4F subshell. So it should be a 6s2, 4F, 4. All right, that completes this activity.